Hey, hello once again, and welcome back to chemistry. Today, we are going to actually go ahead and try to define what is an acid, what is a base. Even though last time I was telling you it's so hard to define what is an acid and a base, now that we have a general idea of what an acidic solution is and what a basic solution is, it'll be a lot easier for us to dig in and identify something as an acid and something as a base. And there are two versions. There are two versions of, or two methods that we use to identify something as an acid or a base based on the situation at hand. So if you're ready, I'm ready. Let's dig into it. So, of course, let's start with defining it, what is an acid and what is a base, because, defining it's really going to help us. So, this dude right here, Arrhenius, he is the one who sort of did all this work a couple, majillion years ago. And he said that an acid is anything that creates hydronium ions. In other words, the only cation ions that it creates are hydronium. That is an acid. So you dissolve something in water, it makes a hydrogen or hydronium, bam, you got an acid. Easy peasy lemon squeezy, right? So that's it. That's all there is to it, right? Well, sort of. Because there's more than one kind, apparently. There's monoprotic and there's polyprotic. Now mono, let's see if you can dissect this little puppy. Mono, well, that means one, right? And for us, since we're talking about atoms and stuff, protic probably means proton. So a monoprotic acid only creates one hydrogen ion, right? Because a hydrogen ion, that thing is basically like a proton. It's just a proton without an electron. That's what a hydrogen ion is. Now the same thing, only slightly modified, is polyprotic. Right, so poly we know means more than one, and then the protic is proton. So the polyprotic is any kind of acid that creates more than one hydrogen ion when you dissolve it in water, and that gives us diprotic and triprotic. That's as far as I'm sure there's probably all the way up to tetra and pentaprotic, but not for us, not for today. All right, so the diprotic you get 2, the triprotic you get 3. So there you go, 4 vocab words. Lock them in your brain, and then we'll move on. So here's how this whole thing works, man. So, and this is why it's kind of important, because these mono, di, and triprotic acids, they're not exactly equal, right? They're all acids, but not exactly. Yeah, not exactly equal. So if we look at this guy right here, HCl, this is going to be monoprotic. Right? Because there's only one hydrogen here, right? So that's pretty easy. If we have 1 mole of HCl, we will have 1 mole of hydronium ions. Very cut and dry, very easy. Now we come up to this one, the sulfuric acid, this H2SO4, right? So this stuff, right? This is diprotic. So what that means is for every 1 H2SO4 that we put in water, it will produce 2 hydrogens, right? So it's almost like doubly acidic. So 1 mole of H2SO4 will yield 2 moles of H3O ions. You see how that works, right? So same thing. This is the same stuff. So it's diprotic. So if I have 1.5 mole of a diprotic acid, that means I will have 3 moles of hydrogen ions in solution, basically, or acidically in this case. I could do this all day, and I will be, so hold on tight. Now, the next one that we're going to look at, H3PO4, this is an example of a triprotic. That stuff is nasty. It's one of the few acids I'm actually afraid to handle. It's evil. Well, nervous. I ain't scared. You know what I mean. So, for every 1 H3PO4 that we put into solution, it will produce, basically, 3 hydrogen ions. So, if I have 2.5 moles of a triprotic acid, I will produce 7.5 moles of H3O ions, right? Yeah, awesome. You guys picking up on this? Isn't, it kind of gives it away. They do have little subscripty thingies right here. So it should be easy to tell if it's a mono, di, or triprotic. And this is really important to start like really honing in on. Not so much right now because we're just looking at them, but once we move further and we start working with acids, it's very, very important to lock in to see if we have monodi or triprotic acids, okay? Because they all act, if you can imagine, kind of different. So pretty simple. Arrhenius acids, they make hydrogen ions. Same thing for bases. Pretty simple, only not exactly the same. They all produce only hydroxide ions when you put them in water. Seems pretty simple, right? Like this one, sodium hydroxide. Now, if you'll notice, there's only one hydroxide polyatomic ion in this compound. So when we dissolve it in water, we only make one hydroxide ion. It's like a 1-to-1. Nice. So if we have 1.5 moles of sodium hydroxide, we will have a total of 1.5 moles of hydroxide ions in the water. So there'll be 1.5 moles of hydroxide ions, making it all basic and stuff. You dig? You see how that works? Lovely. Now let's look at this one. Now this one, again, same thing. Again, only different. Now we have two. We have two ions there. So for every one calcium hydroxide, we will produce two hydroxide ions. Yeah? It works just like the diprotic acids, only it's base. So in this case, if we have 1.3 moles of my calcium hydroxide and it all broke up and dissolved, I will have 2.6 moles of hydroxide ions. That's how many moles of ions I've got there. Got it? Lovely. Let's look at this one. Now this one's a special case. I mean, look, this stuff is weird, man. This stuff is weird because it's NH3 and yet I'm making a hydroxide ion. That's weird. Here's what's happening in the water. If you remember, NH3, the Lewis electron dot diagram looks like this. Right? Okay, so if we take that NH3 and we pop it in water, let's remember now that water is constantly doing this, where we get two waters, it's in equilibrium, making H3O plus OH minus, right? Well, this H3O is effectively a hydrogen ion. It's a naked proton. And since this is right in water, it's right next to water, and so as soon as these two waters collide, instead of that one hydrogen ion, right, embedding itself into the unpaired electrons of the oxygen, it embeds itself because it happens to be right next to a nitrogen. It embeds itself inside these two unpaired electrons of the nitrogen, forming a coordinate covalent bond. Remember that? So we then end up with something that looks like the ammonium ion, like that, right? And the reason, like, where did this hydrogen ion come from? Well, it came from the fact that water is constantly like breaking into it, like smashing into itself and breaking apart. And instead of like landing in an oxygen, because the nitrogen's right there, that little naked proton lands into the nitrogen. And then the hydroxide, just this stuff, just kind of floats away. You picking up what I'm putting down? Lovely. So it turns out the mole-to-mole ratio for ammonia and your hydroxide ions is 1-to-1. It's very nice and easy. So if you have 3.7 moles of ammonia, you will make 3.7 moles of hydroxide. You dig? Now this is one of those cases where ammonia is a base even though it does not contain the hydroxide ion in itself, but when it dissolves in water, it does indeed produce a hydroxide ion. And that's the definition of a base, right? Anything that makes a hydroxide ion when you put it in water. So bam, there you go. Ammonia is a base even though it doesn't have any hydroxide in it, which is weird. All right, so let's check these out. Acid or base? Well, that first one, that's tough. Give me a minute. You know, if you're ever not sure of something, if you dig through these, you're going to find the answer. Oh, like this right here. Table K, common acids. Well, if I look around there, I'm going to see at the very, very bottom, I'm going to see this very compound as an acid. Now, it is an organic acid, so it's a little bit weird. And so I'm doing this first so you know it's in the reference table, so it's going to show up eventually. But what happens is when you put this stuff into water, this hydrogen breaks off, making an acid. So this is an acid. This stuff, oh my gosh. Okay, that's a base. That's easy to see. Oh, there you go. Base, easy to see. And this one, I'm going to bet that it's an acid, but if I'm not sure, I'm going to go to where all the answers are. And sure enough, H2CO3, carbonic acid, this is an acid. This is a really important acid for you guys to know about because this is what happens when carbon dioxide dissolves in water. It's one of the reasons why soda is so very, very acidic. But more importantly, as the carbon dioxide levels in the atmosphere increase, right, the carbon dioxide levels or the carbonic acid levels in the ocean increase, right? Because that whole equilibrium thing, right? Remember, if you increase the concentration on one side, it'll push it towards the other side. So more carbon dioxide in the air means more carbon dioxide in the water. And what that does is it makes the ocean just a little teeny bit more acidic. Who cares? You and me. That's who. Because there are these things called zooplankton that are floating around in the ocean, and they have these little teeny like shells that are made sort of like coral, right? Like coral, they have these but it's teeny. Like these are one cell organisms, right? So inside they've got all their cellular blah blah blah, but what's very special about these things is that they undergo photosynthesis. Right? And these things live in the first like meter or so of the ocean. And everyone's worried about the rainforests being cut down, and that's how we're going to lose our oxygen. But the vast majority of the oxygen that you and I breathe come from these little dudes, these little zooplankton that are floating around in the ocean. So who cares about a little bit of extra carbon dioxide? They would love it because they absorb carbon dioxide to produce the oxygen, right? Right. But it's a little bit balancy. Because when carbon dioxide dissolves in water, it produces the carbonic acid. And as the acidity level increases, as it becomes more acidic, the acid eats away at this little protective shell, and then they're broken apart very easy, or they have trouble thriving. And when they have trouble thriving, so do we. But hey, let's keep things on a bright note, because don't worry, everything will be fine. It's just a hoax. Oh, look at this. Something new. So look, everybody thought that was great. Arrhenius figured it out. You throw something into water, it makes a hydrogen, it's an acid. You throw something into water, it makes hydroxide, it's a base. But then someone was like, yeah, but sometimes not. And here's the problem. Well, the problem was this thing. Equilibrium. Because sometimes reactions went that way, and then they also went that way. And if like one person wrote it like the forward direction is the reverse, and the other person wrote the reverse is the forward, it became very, very confusing. Because forward reactions and reverse reactions, they were like, what is going on? So two separate scientists came up with an answer at this at the same time. This is how we identify acids and bases in a system at equilibrium. And here's you need a whole different system, because a system at equilibrium, you can write it this way or you can write it this way, because the forward, it's like they're both happening, right? So who knows which is the forward or which is the reverse? It depends on how you happen to write it down. It's all about perspective. You know what I'm saying? So they sat down and like, this is what we're going to do. An acid is anything that is able to donate or give up or produce or give off a hydrogen ion. Right? So if it spits out a hydrogen ion, we'll call that an acid. Now the opposite is if it gobbles up or takes in or gathers up or accepts a hydrogen, we will call that a Bronsted-Lowry base. Easy peasy lemon squeezy. So the acid, right? The acid is going to donate. The acid gives up or gives off. The base accepts or gathers or gobbles up. And here is what that will look like. In this case, see how it's like an equilibrium? As this substance goes from here to here, it is going from H3 H3O to H2O. If you'll notice, it went from a 3 to a 2. It gave off a hydrogen. So that is going to be an acid. Now this other one right here, it went from OH to H2O. So it went from OH to H2O. It gathered, it gained a hydrogen. You see how it gained? And so because it gained a hydrogen, it's going to be called a base. You dig? Let's do a couple more just to like lock this in. And what we get here is we get not just an acid and a base, but we also get conjugate acids and bases. Because again, it's a system at equilibrium, and it goes this way and then it goes that way. It all depends on how you write it down on the piece of paper. So here's what we do. We've developed these things called conjugate acid-base pairs, and they're basically two substances that are different by a proton. So the two substances that are different by a proton. So let's look at this at this here situation that we got. And let's start with this HNO3. On the left, it is HNO3, and on the right, it is just flat out NO3. And if you'll notice, this is different by one hydrogen. And these lines, man, I draw these all the time. That's how I can tell that this is going to be a conjugate acid-base pair. Now this one is the acid, right? Because it gave up. It dispersed. It broke off, lost, whatever word you want to use. It lost a hydrogen. See? Right? Lost a hydrogen. So this is the acid. Because in the forward direction, it acts like an acid. Now over here, if it's going in the reverse direction, right? Now when we do the reverse reaction, this stuff acts like a base, right? Because it starts as NO3 and it gobbles up a hydrogen. It gains or accepts. And that's why people are like, what is this? First it's an acid, then it's a base, then it's an acid, then it's a base. So on the left-hand side, we call it an acid or a base. And on the right-hand side, we call it a conjugate acid or base. And for us, the conjugate just means that it's on like the product side. So this is going to be the conjugate base. This is an acid. Its partner on the other side is the conjugate base. Now, the other substance in this reaction, the H2O, becomes an H3O. So this is a base because it is gaining, accepting, or gathering up a hydrogen. It starts out with just 2, and it ends with 3, so this is a base, which makes this thing a conjugate acid. Its partner is the conjugate acid because in the reverse direction, right, as it undergoes the reverse reaction, it goes from 3 hydrogens to 2 hydrogens. It gives up a hydrogen. See? So forward reaction, it's a base. In the reverse reaction, it's an acid. So we call this one the base, and we call the one on the product side the conjugate acid because it is a conjugate acid-base pair. One way it's an acid, one way it's a base. And the conjugate just means that it's been written on the product side. Now if we took this reaction and we wrote it the other way around, it doesn't matter. The product side is always going to be called conjugate. Doesn't matter who's over there. You got it? Okay, so for this one, we've got NH4, and it's going to turn into NH3. So that's one conjugate acid-base pair. And my OH, yeah, that's got to turn to that one. Different by only one hydrogen, so conjugate acid-base pair. Now this stuff right here, I've got 4. So this is donating, so that's got to be an acid, right? Because it's losing a proton. It's going from 4 to 3. So if that's the acid, this has to be the conjugate base, right? And then this stuff right here, it's going from 1 hydrogen to 2 hydrogens. So this stuff is absorbing a hydrogen. So this has to be a base. And if that's a base, then that would make the water, in this case, a conjugate acid. That was easy. I can do that one. I think you can too. I ain't scared for you. Let's try another one, just in case. So let's see here. HBr is not going to turn it. Okay, so it's here, right? Because you notice these two things are different by only 1 hydrogen, right? That one and that one, that one and that one, that one. All right. Okay, and pretty clear that these two are going to be like that. Okay. Oh, you know what? Sometimes that's going to be too confusing to me. I'm going to go like this. That helps my eyes a little bit better. All right, one hydrogen here. No, so this guy lost or gave up, and yep, this guy lost or gave up a hydrogen, so this is going to be the acid, and that'll make its partner the conjugate base. Let me double check. Yep, it's gaining, so it has to be a base. Perfect. Conjugate on the product side. Beautiful. So that means this stuff should act like a base. Yep. This is a base because it's going from 2 to 3, so it's gaining or accepting a hydrogen ion, and that makes its partner the conjugate acid, right? Because it's going from 3 to 2, so it's giving up. I think I'm getting the hang of this. I think I can do this. All right, let me see what this one is. CO3. Yep, this one. These two look like they're partners because they're different by only one hydrogen. And these two are different by only one hydrogen. Lovely. So what is this thing? Is this an acid or a base? It's got no okay, so it's going to gain a hydrogen ion. So I'm going to call this a base. And if that's a base, its partner is going to be a conjugate acid. So let's see, there's 2 here. One, yep, this is giving up a hydrogen, so this has to be an acid. And if that's an acid, this has to be its conjugate base. And it is indeed, because here it starts with 1, here it's got 2. So this thing over here gathers up or gains or accepts hydrogen ions. Man, that's all. Oh, hey, that's all there is to do. 2 different ways of defining acids and bases. Arrhenius, super easy. If it makes a hydrogen ion, it's an acid. If it makes a hydroxide ion, it's a base. But that is only for one-way reactions. Arrhenius is only when it goes one way, a non-reversible reaction. Now the Bronsted-Lowry, that's the conjugate acid-base pair, and we have this one because some reactions are reversible. They can be going this way or they can be going that way. They can be written like this or they can be written like this. So who knows what it is? So the way that we define acids and bases when there's a system at equilibrium, like that, is that it? Yeah. When we have the system at equilibrium, is anything that gives up a hydrogen is your acid. Anything that absorbs a hydrogen is your base. Got it? Acids and bases are on the reactant side. The conjugate acid and base are always on the product side. I think that's enough knowledge for like one day. I'm going to head on out of here. I hope you guys have a super awesome day, and I hope you learn a lot and make your brains really big, like giant, like this is like going to the gym and working out your brain. Get smart. Have a great day.